Last lecture, we considered equations in y equals mx plus b format, i.e. linear polynomials, and we saw that their graphs give us straight lines with a slope of m and a y-intercept with a value b. This lecture will jump up a degree and consider quadratic polynomials. That is, equations that are structured y equals ax squared plus bx plus c. The idea is similar to what we had before. Let's start with a simple example. Consider the equation y equals x squared. We'll graph this equation. As before, we pick sample points for x, and then y is determined by the equation. To start with x of negative 3, y becomes 9, because negative 3 squared is 9. If x is negative 2, negative 2 squared is 4, so y is 4. If x is negative 1, y is 1. If x is 0, y is 1. If x is 1, y is also 1. If x is 2, y is 4. And if x is 3, y is 9. As before, we plot these points on the Cartesian plane and then connect them. We may be tempted to connect these points by straight lines, but in actuality this is a curve. It doesn't consist of straight lines. We only picked a few points. If we additionally picked x equals a half, 1.5, 2.5, and so forth, in between those integers, we'll see that they don't fall on a straight line. The more points we use, the more accurate the picture. For a more accurate graph, we connect these points together through a curve that passes through all of them. And then we get a curve back that overall looks like a U. This shape is called a parabola. Let's look at another example. Let's graph the equation y equals negative x squared plus 2x. We'll pick some values of x and then determine what y is and make a little table below. If x is negative 2, y turns out to be negative 8. Because x squared would be 4, and 2x would be negative 4, so it would be negative 4 minus 4. If x is 1, y turns out to be negative 3. If x is 0, y is 0. If x is 1, y is 1. If x is 2, then y is 0. If x is 3, then y is negative 3. And if x is 4, then y equals negative 8. All of these are done by simply plugging in the x values to figure out what y has to be. Now we plot these points and connect with a curve, and we would get this diagram. This is also a parabola, but it has an upside-down U-shape. In the first example, it had a U-shape. In the first example, the parabola was opening up, and in this new example, the parabola is opening down. In general, in a quadratic equation, y equals ax squared plus bx plus c, that will produce a parabola. Its shape is determined by the sign of the a, which is the coefficient of the x squared. If it's positive, if a is greater than 0, then the parabola will be opening up and has a U-shape, as in the first example, where a had a value of 1. If a is negative, if a is less than 0, then the parabola is opening down and has an upside-down U-shape, as in the second example where a was negative 1. Whenever we have a quadratic equation of y equals ax squared plus bx plus c, we may ask for the y-intercept and the x-intercept. The y-intercept is where the parabola intersects the y-axis. That's easy to find. When the parabola crosses the y-axis is the point that the x-coordinate is 0, so that when x is 0, we are crossing the y-axis. We can find the y-coordinate thus by substituting x equals 0 for the equation, where you have y equals ax squared plus bx plus c, and substitute x equals 0, essentially we get y equals 0 plus c, which is the same thing as y equals c. Therefore, the c is always the y-intercept. In our above two examples, they both had y-intercepts of 0, which is why there is no c term in those equations, because the c term equals 0. How do we find the x-intercepts? That's the place where the parabola crosses the x-axis. This is a bit harder because there might be more than one possible answer. In the first example, y equals x squared, there's only one x-intercept, and that is when x equals 0. In the second example, y equals negative x squared plus 2x, there are two x-intercepts, when x equals 0 and x equals 2. For any parabola, there will either be 0, 1, or 2 x-intercepts. This depends on how the parabola is positioned. If the parabola lies entirely above or below the x-axis, then there will be no x-intercepts at all. If the parabola touches the x-axis, as in the first example, then there will be one x-intercept. If a parabola cuts through the x-axis twice, like in the second example, then there will be two x-intercepts. So the question is, given a parabola of y equals ax squared plus bx plus c, without graphing the parabola, how can we know how many x-intercepts there will be, and how do we find them? Well, we reason as follows. When the parabola cuts through the x-axis, the y-coordinate at that point is 0, so y equals 0. Therefore, we have an equation 0 equals ax squared plus bx plus c. To find what the x-intercepts are, we solve this quadratic equation. Recall that a quadratic equation may have 0, 1, or 2 solutions to it, depending on the sign of the discriminant, b squared minus 4ac. So we can determine the x-intercepts by solving this quadratic equation. Let's look at a couple of examples. Example 1. Find the x-intercepts of the parabola y equals negative x squared plus 2x. This is the parabola we graphed earlier. Visually, we can see that the x-intercept occurs where the x-coordinate is either 0 or 2. But we can also get this result algebraically by solving for the equation negative x squared plus 2x equals 0. We may be tempted to use the quadratic formula, but it's not necessary since we can easily factor it. We can factor out an x and get x times negative x plus 2 equals 0. Now set each factor to 0. One solution is x equals 0, and the other solution is negative x plus 2 equals 0, and in that case x equals 2. Therefore, there are two x-intercepts, one at x equals 0 and the other at x equals 2. Second example. Find the x-intercepts of the parabola y equals x squared plus 2x plus 2. We need to solve the quadratic equation x squared plus 2x plus 2 equals 0. When we try to use the quadratic formula, we will note that we will get radicals of negative numbers. So the quadratic equation has no real solutions, which means that the parabola does not intersect the x-axis anywhere, so there are no x-intercepts. Another way to see this is to compute the discriminant, b squared minus 4ac, which is 2 squared minus 4 times 1 times 2, which is 4 minus 8 and comes out to negative 4, which is a negative number, so that there are no solutions to the quadratic, which means there are no x-intercepts. Next, let's learn how to find the vertex of a parabola, which is the same thing as the turning point, or the highest point in a parabola that opens up downwards, and the lowest point in a parabola that opens up upwards. Using a derivation of the quadratic formula, we can deduce, in a way that we don't really have to discuss, that the vertex of a parabola is where x equals negative b over 2a. Recall that b is the coefficient of the x term, and a is a coefficient of the x squared term. Let's look at a couple of examples. Find the vertex of a parabola of y equals negative x squared plus 2x. We already graphed this parabola before, and we can see in the picture that the vertex occurs where x equals 1. But we can also get this result easily by applying our formula, negative b divided by 2a, which is negative 2 divided by 2 times negative 1, which is negative 2 over negative 2, which of course is 1. We get the same answer. If we want to get the coordinates of that point, we also need to find the y-coordinate, as we have x equals 1, and we can substitute into the equation y equals negative x squared plus 2x, and we get y equals negative 1 plus 2, which is 1. So the y-coordinate on the vertex is also 1, which means that the vertex coordinate is located at 1, 1. This is the turning point of the parabola. Another example. Find the vertex of the parabola y equals x squared plus 2x plus 2, another equation that we dealt with before. Instead of graphing this and trying to find where the vertex occurs, we can simply use the formula x equals negative b over 2a, or negative 2 over 2 times 1, which is negative 1. Therefore, the x-coordinate of the vertex is negative 1. And to find the y-coordinate, we substitute y equals negative 1 squared plus 2 times negative 1 plus 2, which is the same as 1 minus 2 plus 2, which is 1. Therefore, the parabola has a vertex coordinate of negative 1, 1. Given a parabola of y equals ax squared plus bx plus c, if a is positive, or greater than 0, then the parabola has a u-shape, so its vertex is the minimum point, or the lowest point, on the parabola. If a is smaller than 0, or negative, then the parabola has an upside-down u-shape, so its vertex is a maximum, or highest point, on the parabola. Using these ideas, we can solve some simple optimization problems. An optimization problem is a problem where we need to find the optimal solution, being either a minimum or a maximum, to some problem. Here are a couple of examples. First example. An architect has 12 yards of fence. He wants to design a rectangular fence with the largest possible area. How should the fence be built? As an illustration, the fence can have a length of 5 yards and a width of 1 yard. So we're using a total of 5 plus 5 plus 1 plus 1 equals 12 yards. This type of fence will have a total area of 5 square yards. Or consider the fence with a width of 4 yards or a length of 4 yards and a width of 2 yards. So we're using 4 plus 4 plus 2 plus 2, which is 12 yards. This type of fence will have an area of 8 square yards. This is an improvement, but is it the optimal such fence? Can we build a better one? How about a square fence, where each side is 3 yards? Then such fence will have 9 square yards of area. Even better. It turns out that a square fence is the best possible fence. But how do we get this? Well, let's look at it as an equation. Let x equal the width of the fence. Therefore, since there are two sides, x plus x, or 2x yards, will be used on building the width of the fence. The remaining two sides, which we'll call the length of the fence, are therefore 12 minus 2x yards, since the fence has a total length of 12 yards. Of course, the convention is to call the length the longer side, but it really doesn't matter. As long as you're consistent, you can call either direction length and the other direction width. So one dimension was 2x. The other dimension would be a total of 12 minus 2x yards. That means, because you have to divide it up amongst two sides, that length would be 12 minus 2x divided by 2. Now 12 minus 2x divided by 2, by dividing each side by 2, can be further simplified into 6 minus x. So one dimension, let's call it the width, would be x. The other dimension, let's call it the length, would be 6 minus x. The area is the length multiplied by the width. So the area is x times 6 minus x. And we can multiply it out to 6x minus x squared, or negative x squared plus 6x. Either way is the same thing. So we can apply the formula, the area equals negative x squared plus 6x. That describes the area A of the fence in terms of its length and its width. If its width is 4, then the area would be negative 16 plus 24, applying that formula, which would be 8. If the width is x equals 5, then the area is negative 25 plus 30 equals 5. We want to optimize the area. We want to find the largest possible area A. Note that A equals negative x squared plus 6x is a quadratic polynomial with the A value being negative 1, which is negative. So this is a parabola which has an upside-down U shape. In particular, a maximum point. We wanted to convert this into an equation with a negative a because then we would have a maximum. If we'd have a positive a, of course, then we'd have a minimum, which really wouldn't help us get what we're looking for. The maximum point in any parabola occurs at its vertex. Since a equals negative 1 and b equals 6, the parabola of this the vertex of this parabola occurs at negative b over 2a, which is negative 6 over 2 times negative 1, which is negative 6 divided by negative 2, which is 3. So the width is 3. And because the width is 3 in this case, the height also has to be 3. That's dictated by the amount of material, which means that the optimal area in this case is a 3 by 3 square. So now we know how to solve linear and quadratic equations, as we've discussed that over the last few lessons. In those cases, there was only one variable, usually called x, to keep track of. Next lecture, we will consider a system of equations. We will have two variables and two equations. For simplicity's sake, we're going to start with linear equations. And we will look at both algebraic methods and graphing methods for solving these systems of equations.